Okay, guys, we're in algebra again, day 6, end of week 3. So we're starting a new unit today, and it's all about everyone's favorite subject. That's what I thought. Graphing on an XY plane. And believe it or not, this actually started in geometry because they were trying to come up with ways to show things in multiple dimensions. Graphing is used all the time in all kinds of industries, but it's not rocket science though either. So before we dive into that, anybody got questions? So everything that we're going to look at today, with the exception of one handout, is in your materials. All I have to do now is find it. Here's where we start talking about a two-dimensional coordinate plane. When we were doing the inequalities, the single variable inequalities, that was on, well, that's hard to see. That was on a single number line, just like the traditional horizontal number line from right to left or left to right. Now we're talking about a combination of two number lines, one that's horizontal and one that is vertical. And if you travel much and have used, most of you are probably too young to have used paper maps. That's what we're doing. We are mapping points on a graph. Paper maps work the same way. You've got a coordinate from one direction and a coordinate from another direction, and you can identify the location. The example that I use for this subject all the time is right here in Noblesville. If you're familiar with how Noblesville is laid out, Connor Street runs all the way across town. It's State Road 32. If I told you, asked you to come pick me up out on Connor Street, you could be driving all the way across town. You wouldn't have any idea where I'm at. But if I told you to pick me up at 17th and Connor Street, which is an intersection, now you know where I'm at. You can put that in GPS and find me right away. Or just follow the layout of the streets, and eventually you'll get to 17th Street. 17th Street is the street right out here in front of the school. And these coordinate plane maps are exactly like that. We got to have two identifiers in order to pick a point that's actually on the map. We're going to be talking about key parts of this coordinate plane. We're going to do what's called plotting, P-L-O-T, that word right there, the third word in the second bullet point. We're going to plot an ordered pair. Well, it's called an ordered pair because it comes in a specific order, and it's a pair of numbers. It's always X, comma. Every point that we plot on the map is going to have two numbers, X followed by a comma, followed by a Y. Later on, this unit will be figuring out whether or not a graph actually represents a function. A function is a specific kind of relationship between terms. The example I use for functions a lot is like a soda machine or a candy machine. You put your money in, you press a button. What you get out is a function of the button that you press. It's not an unknown. It's not some magical thing where you could get this or you might get that. If you want M&Ms, you press the button for M&Ms, put the right amount of money in. What you get is a function of those two things. So we're going to be looking at graphs as functions also. Sometimes one thing will depend on another. One thing will be a function of something else. And here's the guy that's responsible. René Descartes, Frenchman, lived in the 16th and 17th centuries, long time ago, 400 years ago or more. He's probably most famous for the phrase, "I think, therefore I am." So he wasn't just a mathematician. He was also Oh, that sounds good. Whoever's drinking out there. Need to mute yourself though, okay? No, it had ice in it. There was something with ice in it. So he actually brought graphing from analytical geometry and originated the Cartesian coordinates and Cartesian curves. Thankfully, we don't have to worry about curves. The only things that we're going to end up graphing this term are straight lines. They're points or straight lines. Cartesian relates to mapping. Descartes, they all have that same word root in them. And so because he's responsible, he gets the credit for this Cartesian plane that we're going to be graphing on, that XY plane, the set of coordinates. And here's what this Cartesian graph looks like. It's showing Roman numerals, 1, 2, 3, and 4 in a counterclockwise orientation. If you start at 1, you're going to go left around the clock. The primary purpose for those quadrant identifiers is to help you remember signs. If you break this down, you've got the x-axis going across here horizontally. You got a middle point there, that's 0. To the right are positive numbers, to the left are negative numbers, just like a traditional number line. That's called the x-axis. The vertical line is another number line. This one's called the y-axis. When you go up, the numbers are positive. When you go down, the numbers are negative. That's more like the thermometer style of a number line. Because when you go below 0, it's getting colder. Numbers are getting lower and lower, farther below 0. So in order to plot a point on here, we got to have an X movement followed immediately by a Y movement. And so anything in this first quadrant, quadrant 1, is going to have both of those terms. Both of our numbers are going to be positive. Because if we go to the right on X, it's positive. When you go up from there on Y, it's also positive. Quadrant 3 is exactly the opposite. Left on X is negative, down is also negative. So everything in quadrant 1 is plus plus, everything in quadrant 3 is minus minus. When I talked before about the importance of signs, it's really amplified here with graphing on this XY plane. 2 and 4 are also opposites, but they're mixed. So if you're in quadrant 2, you're going to go left on X, up on Y. So 1 is negative, up is positive for Y. So you got minus plus. Quadrant 4 is exactly the opposite. We're going right or positive on X, but down on the Y axis. And if you notice, every one of these, I did the movement on X first, whether it's left or right. And that's the way these ordered pairs work. The first number is always X. The second number is always Y. If you look in this second paragraph, this point 0, 0 is where both of those number lines cross. That's called the origin. That's where we start every time we're ready to put a point on a graph. We go to that origin and then we start our movements. On X first, that first 0 is how far we go on X. The second 0 would be how far we go on Y. Well, we don't go anywhere from the origin when it's 0, 0. But the ordered pairs will follow that, any other points that we plot on here. And we're going to look at a bunch of those here in a minute. Anybody got questions so far? Some more vocabulary. Two of these things I've already talked about, the x-axis and the y-axis. And I mentioned the coordinate plane. That's just in general, that's the graph that we're putting these on. Here we got the origin again at 0, 0. Long paragraph here about what an ordered pair actually signifies. And then the third line there, you see it is written in the form of x comma y. X is the x coordinate, be like Connor Street or 17th Street. Y is the y coordinate. The x coordinate always tells you where to go first. And the thing to remember here especially is you do these one after the other. One immediately follows the other. You're gonna do your movement on X and then immediately go the direction that tells you for Y. You don't go back to the origin. You don't end up with two different points on a graph just because you got two numbers. It's X followed immediately by Y. That gives you the ending point where you're going to put a dot on the map. Here's exactly what I'm talking about. We've got a graph. Scale is up to 10. Can anybody identify that ordered pair for me? Close.
5x, 5, 6.
5, 5, 6. Start at the origin, go to the right. Okay, I stop at 5. So that's my x value. No, not 5x, just 5 comma 6.
Oh, okay, that's right.
We don't use the letters when we're talking about the ordered pair. We know automatically the first letter, the first number is x. The second number automatically is y. So that's why when I'm talking about ordered pairs, I try to always say 5 comma 6. Because that'll tell you that it's an ordered pair. It's not 5, 6. 5, 6 could be 56. I could just be counting 5, 6. But when I say 5 comma 6, that's how I identify an ordered pair. So from the origin, I went to the right 5 and immediately up 6, and I got to that point, 5 comma 6. So that's one example. 4 comma 9. Negative 5 comma negative 7, negative 2 comma 6, 8 comma negative 8. How much you want to bet that one of those ends up in each quadrant? No, that's not really what I'm asking.
I was talking about, sorry. Yes. They will all
That's a good try.
separate.
Before I even plot these, if you think back to the quadrant identifiers, remember everything in quadrant 1, both numbers are going to be positive. So this first one's going to be in quadrant 1. 4 to the right, 9 up. 4 comma 9 is going to be right there where the arrow is, where I put the arrow. The opposite one's going to be down here. Left 5, down 7. Quadrant 3. Quadrant 2 is the next point. Negative left 2, up 6, and then finally 8 to the right, down 8. So they're just doing it this way to show you where you would find one point in each of the quadrants. So pay attention to these signs. Quadrant 1, all positive. Quadrant 3, all negative. Quadrant 2, X is negative. Quadrant 4, Y is negative. Questions now, anybody? All right, so the purpose of this particular graph is to give you some practice identifying these ordered pairs. We're not even worried about drawing any lines. We're not trying to connect the dots or do any of that sort of stuff yet. The first step in all this graphing on the XY coordinate plane is to make sure we can get the points on the right locations on the graph. So it gives you the first one, letter A, capital A is right over here, 3, 3. I know there's no numbers on this graph, but if you look at the dark lines, the dark center line, left and right and up and down, where they intersect, that is 0, 0. That's the origin. Over to the right here from the horizontal dark line there, it says X. So that's identifying the X-axis, and above the vertical line, it's got Y. So that's the Y-axis. And that's going to be true for all these graphs pretty much here throughout any other math that you're involved in until you get into three-dimensional stuff, if you get that far. So what are the coordinates for letter I?
-5,-7.
Okay, we got 2 votes for 5, -7.
Yeah.
Sounds correct. Got 1 here in class from Jaden. And who was that at home? Is that Esma?
Sama.
Sama. Okay, thank you.
You're welcome.
All right. So the next one, G, that's way down there in quadrant 3. -9, -9. Everybody agree on that?
Yes.
All right, good. C. 7, -2 is one vote, but that sounds backwards to me. Right.
-2,
Yep.
-7.
-2, 7. Right. Got to get that X movement in there first. And my favorite letter, of course, is going to be J.
It's 0, -3.
0, -3. 0, -3. That's correct. Yep. If we had a line running through that point, that would be our y-intercept, because that's where we're sitting right on the y-axis. So anytime you see a point that's on the axis, one of the 2 numbers is going to be 0. In this case, for letter J, we have not gone left or right at all, right? Left 0, right 0. So our X value is going to be 0. Then all you got to do is go down to the point, and that gives you the -3 for the Y value. Good job. Now, N. I'm hearing -8, -3 from in here.
-8, -3.
Okay, seems like it's consensus. Now, the hard part about this graph and this handout is when I have to start shifting it to see the bottom half of the screen, because then I lose part of the graph. Okay, so it's the second grouping. Now it's giving us the ordered pair, and we have to guess, we have to identify the letter correctly. So F is up at the top. That's the first one. I'm going to scroll past that. So what letter goes with -4, -5? B as in boy? Everybody okay
Yeah,
with that?
B. Yeah.
What's the matter, Jaden? You disagree? You just, they are both negative.
Yeah, so would be,
-4, -5.
you want the letter, that's.
I'm looking at the wrong one.
Okay, that's all right. You're jumping ahead. Sounds like you're maybe looking at 9.
No.
He's thinking the quadrant.
Oh, okay. Yeah, I like letter B on that one too. 9, -7, 6. So we go left 7 and up 6, and that puts us right at letter L.
L.
L, yes. Sounds good. I like that. Looks like number 10 is another one that's sitting on one of those axes. E, it's got to be E. Compare what you had for letter J, and you can see that the letter, the values for the one that's 0 has switched. On J, our X value was 0. Now on E, our Y value is 0 because we're sitting right on the X axis. Okay, number 11, 1, 5. M. Good. Excellent. So 12, 7, 2. Okay. 13 and 14. These are going to be fun. These are the best ones on the whole page. The coordinates are opposites. Okay, in which of the quadrants do we have opposite signs? We're going to be in quadrant 2 or quadrant 4. So there's one point where the coordinates are opposite signs, but the numbers are the same.
H.
H. Hallelujah. H for hallelujah. That's right.
Oh.
H for hooray. Very good. Because we go left 3, so that's -3, and then up 3, so that's +3. That's our opposite situation with the same numbers. You got a negative and a positive, both 3s. Very good. 14, though, is probably the biggest brain teaser of all of them on this sheet. The coordinate, the Y coordinate is 5 times the X coordinate. And I'm gonna switch here for just a quick second and write I'm gonna write an equation out real quick that might help illuminate this one a little bit. The Y coordinate is 5 times the X coordinate. Y equals 5X. That equation that I just typed out there, Y equals 5X, is the interpretation of the words that are there with problem number 14. The Y value is 5 times the X value. So there's one point on there that meets that criteria. Kathy says M, and that's perfect. Very good. How'd you figure that out? 5 times 1. That's exactly right. And the X value, you go 1 to the right, so that's the X value, and then 5 up. There's your Y value. That's 5 times more the X value. And the reason, and I'm going to go back to this equation here real quick because we will be doing this a lot over the next couple of weeks. With this equation, Y equals 5X. That's a one-step equation. Now it's 2 variables, but it's still the same process. We can plug some numbers in here, and our value for Y is going to depend on what we put in here for X. We can say X is anything that we want it to be. I'm going to jump ahead a little bit here and do something that I like to call, and lots of people call, it's not just something I came up with, a T-chart. So if I start to do some substituting, this is a function equation. If If I start to substitute some numbers based on that equation, my y value is always going to change depending on what the x value is. So if I plug in a 1 for x, it's going to give me a 5 for y. This is a function in its purest form. Y is a function of x. You don't even know what y is unless you do something with the x value. So the only possible ordered pairs are going to follow that same pattern. They have to be in that pattern in order to remember our solutions for equations or things that give us true statements. So when I start doing substitutions with x value, 5 times 2, y equals 10, 5 times 3, y equals 15. There's only one point of this combination that is actually on the graph that we're looking at. And that's the one that Kathy identified. Get this enlarged again. 1 over 5 up. If we went 2 over, can we get to 10? 6, 7, 8, 9, 10. That's right at the top of the graph. 3 over, 15 up, way off the graph. But the thing, if we could put those points on there, they would start to line up, start to look like a straight line. You put enough points in that equation for x and generate enough y values, you're going to end up with a straight line, which is what we will be graphing. And that's why these are functions, because we can create straight lines with them. The last grouping there just talks about what quadrant or what axis each point is on. I don't think we need to spend any time on that right now.
One I had a question. What did you say, like for 18, if it's on the line, on the y, what quadrant would you put for that?
That's not in a quadrant.
So you leave it blank?
Nope. Just read what this says right here. Name the quadrant or axis. That letter J is on the y-axis, because the y-axis splits the quadrants.
Yeah,
That's the separator. It's okay. A lot of people don't. That's a good question though, because that's a valid point. You want to be sure you understand the difference between the quadrants and the axis. You know, the axis is not in either quadrant. It's just like right on the line. The line is the separator. Any other questions? Guys feel comfortable with how the ordered pairs are put together now? Hopefully. Which actually, now we're getting into the actual graphing part. Coordinate plane graphing. Bunch of new vocabulary. Maybe not new, I don't know. If you've been involved in any kind of construction, you know about slope. If you think about home building, the roof at your home has a slope on it. That's so that the snow and ice won't accumulate. It'll melt and drain off, and it won't cause your roof to collapse. Roads have a slope. If you had to build a wheelchair ramp to get into your house, that's got a slope. The little access points for on the crosswalks here at intersections and corners, those all have slopes. Does anybody follow the Tour de France bicycle race in the summer? They're always talking about the slope on those mountains over there. So for us, slope is going to be an indicator of how flat a line is or how much it's standing up more vertical. We're going to know how to define y-intercept and x-intercept. This third bullet point is a really, really big one, because For us, when we're doing these graphs and we create a straight line from an equation, every point that is on that line is a solution to that equation. Now, thankfully, most of the time we're only going to be dealing with whole numbers, but even the in-between numbers would generate points. You put enough points together, you're going to end up with a straight line using the same equation. So can you identify your point on the graph, and does it give you a true equation when their coordinates are substituted in? And that's what I was doing on the whiteboard a minute ago when I had that T-chart and I was plugging in values for x in the equation y equals 5x. And because that was the equation that was generating an ordered pair for me. Next, we've got the slope-intercept form of a linear function. There's probably at least 5 different words on that line that people might struggle with. But you got to remember this equation here, y equals mx plus b. This is the most commonly used form of equation for our straight lines that we will use. There are 3 different ones. This is the one that we use, I'd say probably 90% of the time for everything that we're going to do the rest of the term, essentially. Slope-intercept. The reason it's called slope-intercept is through the letter M. M represents the slope. So for us, in any of these equations, you see the letter M, you know it's talking about slope. The letter B represents the y-intercept. That is the y value for where that line crosses the y-axis. It intercepts the y-axis at point B. In other words, when x is 0, y equals b. And so that gives us the y-intercept. That y-intercept is where we start our graphing, because that's if all we have is an equation, that's the only point that we know for certain is on the line. Y equals mx plus b. Mx, remember that's multiplication. When you have those 2 letters right together, that's m times x. Sometimes we will actually do that multiplication. Like if we're trying to figure out what the y-intercept is and we have the slope and we have a point, well, we will do a calculation using this equation form to figure that out.
So m times x is the x axis.
No. M is the slope. The y and the x are permanent parts of the equation. They will not change. The m and the b will change. M is going to give you the slope for a particular line, whether it's flat. If you have a flat line, it's a slope of 0. When we talk about slope here in a little more detail in a minute, maybe that'll make more sense. And I've got some drawings in here too to show you. But the only time you'll be doing the actual multiplication is if you're trying to find something that's missing from your equation. Here's the next style of linear equation, standard form. AX plus BY equals C. I don't know why they came up with the name standard form, because it's anything but standard. We don't hardly use this at all for this unit, but the last unit of the term, we will use it a lot. The problem with standard form, it does not give us the slope. It does not give us the y-intercept. We need those two things to help us graph. There are other ways to graph standard form equations. We could solve that standard form equation by solving it for y. And for those of you that are struggling with the literal equations, converting standard form to slope-intercept is a perfect example of why we have to know how to do that. Because standard form doesn't give you what you need to graph, but it can be converted to slope-intercept by solving it for y. You're going to move that ax term to the right-hand side, then you're going to divide everything by b. Move and divide. The third form is called point slope. This one has m in it, so you know that's the slope. Where you see the x1 and the y1, those are actually the values from a point. And that's why this equation is called point slope. Because we could take the slope and plug it in here for m, and then take the x and the y value and plug it in here for x1 and y1. And we can convert this one also to slope-intercept if we solve it for y. The plain old y and the plain old x, those are permanent parts of this equation. The x1, y1 designations are there to identify them as they are from a specific point. That's not my favorite of the equations at all, for a couple different reasons. The first reason is because the y value's in front. You're gonna get tired of me talking about x comma y, x comma y, x comma y. Well, how come we got the y value in front here, Mr. Alley? I don't know. That's why it's confusing. I don't like it either. And because both of these parts of that point slope equation involve subtraction, whatever numbers you plug in here for x1 and y1 are going to change signs. So now you got to reverse the order. You got to change the signs. It's too many extra things to try to remember, in my opinion. But for some situations, it's perfect. If all you have is a point and the slope, and you want to write an equation, this one is tailor-made for that. Here's where we start talking about all the different ways we can describe slope. The little light blue box up to the right, it says vertical change over horizontal change. The change in y over the change in x. Rise over run. Delta y over delta x. Okay, that's 5 different ways I've described slope. And m, oh yeah, I forgot m. It all means the same thing. It's by definition the ratio, and what's a ratio mean? It's a fraction. The ratio of the vertical change to the horizontal change. So if we have a slope of 5 over 3, that means we're going up 5 and over 3 for every point that's on that line. Up 5 over 3, up 5 over 3. We're not going to put these numbers into a calculator and come up with something that's got a decimal in it. We need to keep our rise and run numbers in a fraction form, because that's helpful when we start graphing. The top number tells us how far up and down to go. The bottom number tells us how far left and right. And we start at the y-intercept. So it's all about steepness. Oh, there's Mr. Descartes again. See him a little bit better on this slide. Okay, I got an ordered pair here. It's a clear dot over there at 5,6. Nothing new there, but now there's types of slope. And I didn't come up with these little skiing bird graphics, so don't blame me. I don't particularly like them either, but they are memorable. The good news is there's only 4 types of slope. And the thing I want you to get used to, when you see one of these graphs, positive slope goes up to the right. I don't care what's going on down below the x-axis. Just ignore it. But if you think about our quadrants, everything up in here is positive. Everything down in this quadrant is negative. So if we're going in that direction, if we're dividing positive by positive or negative by negative, what do we get? We get positive. Up to the right, positive slope. That's one of the types of slope. So what do you think up to the left's going to be? Correct. And what's really dumb about these little skiing birds, see, they turned him around and like he's skiing downhill. Well, he could have done the same thing on the other one. He could have been skiing downhill on the other one.
Well, no, you warm it up.
Okay.
Okay. So up to the left, again, ignore what's below the x-axis. Look at where the line is going up and out of the graph. That's going to tell you if it's negative or not. The same kind of reasoning, though, if you look at the quadrants, that line is cutting through quadrant 2, which is mixed signs, negative, positive, and quadrant 4, which is mixed signs, positive, negative. So what do you get when your signs are mixed in a division problem? You get a negative. So positive slope up to the right, negative slope up to the left. Make yourself some drawings that you can refer back to. Try to do something to get those locked into your memory. Zero slope, no slope. The slope, the number is actually 0. If you think back to these other types of slope, if you pick a point on this line and I go up and over, there's the rise and the run is left to right. Well, when you have a perfectly flat horizontal line, there is 0 rise. This line is not going up or down at all. It's totally across this graph where y equals -1. And it uses every single x value. But because it's flat, it has no rise. Remember, all of these slope calculations are based on rise over run. Rise divided by run. The change in y over the change in x. That rise, that change in y is 0, so our slope is 0. The fourth style is the vertical line. Totally straight up and down. The horizontal line had 0 slope, but infinite run. Now, excuse me, not 0 slope, 0 rise and infinite run. Here with the vertical line, we've got infinite rise, but 0 run. So now their bottom number in our slope is 0. There's no way to define how to divide by zero. So that's why this one is called undefined slope. Don't call it infinite. Don't call it definite. The word is undefined. It is an undefined slope.
And you still have the number over zero.
It's infinite over zero. Do you know the symbol for infinite? What'd you say, Jaden? Good. An 8 or a almost like a fish symbol turned on its side. Very good.
And then the zero still have the zero on the top and then infinity on the bottom.
Yep. You can try to divide zero all you want by any number, but it's still zero. Because you got nothing. I don't care what you try to divide it by, you still got nothing. But to do division, you have to try to divide by something. That's why nobody can define how to divide by zero, because you got nothing. You're trying to divide it into some parts. Well, there aren't any parts. So how do you define that? No mathematician has ever been able to come up with an answer for that. Even with a regular fraction, it's still called undefined. Now we get to the intercepts. Any Colts fans here? You know, NFL stands for not for long.
I like the Bears.
Okay, Bears fan, that's good. I remember my first team. Well, if you're a football fan, you know what an interception is, and that's not a good thing. It's where a defensive back or somebody cuts in front of the receiver, runs through there and steals the ball, catches the ball instead of the offensive guy. Intercept is kind of like that, where we got a line running through the graph and it's intercepting the y-axis at a particular point, or it's intercepting the x-axis at a particular point. These first two examples, positive and negative slope, the intercepts here are both zero because it's going right through the 0, 0 point. The zero slope line, the horizontal line, only has a y-intercept because it's running through the y-axis here. The undefined slope line typically only has an x-intercept because it's sitting at x equals -2. So most of the time you're going to have two intercepts, unless it's either a zero slope or undefined slope line. And here's what I'm talking about with the intercepts. And when we were plotting those points, I mentioned that one of the values was going to be 0, and then it would flip depending on which axis the line was cutting through. So the y-intercept is where we cross the y-axis. So our x value is going to be 0. Our y value is wherever that line crosses. The x-intercept is going to be exactly the opposite. -3 in this case, 0 for y, because we have not gone up or down. The x-intercept we don't have to worry about very often. Y-intercept we will use all the time, mainly because in slope-intercept form, it's actually a point that we can put on the graph. When we have a slope-intercept equation, we know that number where b is, that's our intercept. We can actually plot that on the graph. That helps us do the rest of the graphing. So we got all three of these forms of the line: slope-intercept, standard form, point slope. You'll get used to seeing and hearing those terms. There's also, before I go on to the next one, in your materials, and I have to pause this for a minute. In your materials is what's identified here as still called end of course assessment, iStep Plus reference sheet. Most of you don't have to worry about that anymore. And for us in algebra, we only have to worry about these top two boxes. This top one here gives you all those forms of the line. The one starting on the left, you got slope intercept. It tells you again that M is slope and B is the y-intercept. Point slope is in the middle. M is slope, x1, y1 is a point. And then standard form. Right below that, one of the most helpful calculation formulas that you will use in the next 2 weeks is this slope formula, where we've got 2 points, and these x and y values here, x1, y1, x2, y2, that we're not talking about exponents. Those numbers, they're subscript. They're, you know, exponents are up above our numbers or letters. These are subscripts. They're down below. These are there only to identify a specific value from a point. So x1, y1 is the ordered pair for 1 point. x2, y2 is the ordered pair for another point. If you had 3 points, you do x3, x4. X3, y4. x3, y3. If you had 4 points, you do x4, y4. I don't know why I couldn't say that. But it's just an identifier. And so this little calculation here, y2 minus y1 over x2 minus x1, is a way to find the slope when all you have are 2 points. That's another one of these ways we define slope, is with that little calculation. So if you have the opportunity to screenshot this or print it out, I would encourage you to do that, because this will come in handy the rest of the term. We'll be using all of these. Anybody got questions? All right. Now I got to get back to where I was. Solutions. This is kind of where the rubber starts to hit the road for graphing. Asking if something is a solution. Okay, there's 2 ways we can figure that out. Anybody want to take a chance on identifying one of the ways? I'm sorry, say it again. Similar. Same kind of idea, if I understand what you meant when you said one-step equation. This is actually a 2-step equation. It's a 2-variable equation. My other one that I used before, the 1-step y equals 5x, that was a 2-variable equation. Solutions for linear systems. What that means is any point on the line is a solution. So here we have a point. We've got the point 3 comma -2. We've got an equation. It's in standard form, x minus 3y equals 9. And we've got a graph. So since our solutions must be on the line, how can we determine if that point is on the line? Well, anytime you got the graph, it's going to be easier to figure this out. We know how to plot points now, just plot the point. No, our point's up here. It's in this paragraph. It's the point is 3 comma negative 2. Don't worry about the equation right now. I just want to know where this point is. 3 negative 2.
Okay.
3 to the right, 2 down. Looks like I'm hitting right on the line. Where my arrow is now. If I put a point right there, that's the point 3 comma negative 2. That looks like it's on the line to me. So I could say, yeah, that's a solution. Because any point on the line is a solution. If I'm a little hesitant, let's take that point and plug it into the equation. I got an x value in the point, that's 3. I got a y value, that's negative 2. So substitute 3 for x from the point, negative 2 for y from the point, so that's negative 3 times negative 2, that's 6. Add it to 3. I didn't want to go that direction. Why did I do that? Here's what I'm talking about by the substitution. X minus 3y equals 9. X is 3 from the point, so I can replace the x.
So then it would become 3 minus 3 times negative 2
Yep, because that
equals 9.
negative 3y is multiplication, correct.
Okay.
So is that true? I think it gets to 9. Negative 3 times negative 2 is positive 6. Add 3, got 9. I got 9 equals 9. True statement. Confirms what I plotted when I put the point on the graph. And that substitution that I just did is probably one of the most common solution techniques that you'll see the rest of this term. You'll hear us talking about substitution. If you see x in an equation and you've got a point that you know is an xy point, you can substitute all day long the x for the x, the number for the x, the number for the y. Don't mix them up. Don't put the y value in where the x goes. But wherever you see x, it's going to refer to the same thing. You know, if it was a capital X, then we don't know what that is because that's not part of this linear equations stuff that we're working on right now. But if it looks the same, it is the same. So let me blow this back up again. Here's the next one. We got another point. Negative 2, negative 2. Is that a solution? We got a different equation. What do you think? Okay, I hear a no. And I think I know why, because if you go left 2 and down 2, you are nowhere near the line. And again, with the graph, work with the graph anytime you can. You can see it. It's easier for a lot of people to use the graph than it is to do calculations. So take advantage of the visual aspect of this and use the graph. If you got to put a point here, draw a point there where negative 2 is to confirm it, go for it. You can do the same substitution. Negative 2 plus negative 2 is not 2, it's negative 4. So negative 4 does not equal 2. So we don't have a true statement. So mathematically, we can also show that it's not a solution.
So on homework and quizzes and stuff, how would you answer that? Would you just put no solution? Means it's not on the line.
It's not a no solution. That point is not a solution. We got a red line drawn on this graph. Every point on that red line is a solution to that equation. Every single point on that red line is a solution. So when a problem asks you about a specific point, you can't say that there's no solution, because every point on that red line is a solution. That one specific point that they're asking you about is not a solution, because it's not on the line. It's not no solution. No solution would mean there was no possible solution. We got a red line that shows us there's an infinite number of solutions. Does that make sense? Something that's not a solution is not the same as saying that there's no solution. They don't mean the same thing, because the solution to that equation, x plus y equals 2, is everything on that red line. Okay? And because negative 2 is not on the red line, that one point that we're being asked about is not a solution. It only applies to that one point. We can pick 0, 2, 1, 1, 2, 0, 3, -1, 4, -2, 5, -3. I can go on and on and on that red line. Every one of those points is a solution. The one they're asking us about is not a solution. That doesn't mean that there's no solution. We have an infinite number of solutions, but only the ones that count are on the line. Nothing else. All this blank area out here, above and below the line, none of those other points are solutions, because they're not on the line. They got to be on the line to be a solution. Same question, different equation, different point. Now we also have the equation written in function form. F of x means the same thing as y equals 2x minus 1. We got a function of x. That function is 2x minus 1. When we plug in a number for x, we should get y. That is the function. So if I plug in 2 for x, 2 times 2 is 4, minus 1 is 3. 3 is our y value from the point. So I'd say, yeah, 2, 3 is a solution. I can also plot it on the graph. 2 to the right, 3 up puts me right on the red line. But 0, 6 is not a solution. If I put a point right up here at the top of the graph, that's not a solution. It's not on the line. -5, 3 is not a solution. 5, -2, that's not a solution. I can come up with as many points that are not solutions as I can come up with points that are, because it's an infinite set. Because you got to remember, this line here, in theory, is not just in this little box. It goes on forever in both directions. So this one is an easy one because it gives you the y-intercept. X is 0, y is 3. It's right there, 0, 3. How about this one? 5x minus y equals 5. We've got this point 1, 1. Is that a solution? No, I like your second answer. 1, 1 is, it's just off the red line. It's close, but no cigar. Close does not count in algebra. It's got to be right on the line. And it's not on the line, so I don't even need to do the calculations. But if I did, 5 times 1 minus 1, 5 minus 1 is 4. 4 does not equal 5. Numerically or graphically, we can determine solutions. How about now? Questions, anybody? All right. The other slideshow it's in the materials is all about slope. Slightly different graphics, same skiing birds. This screen tells you some of the different ways that we're going to learn how to find slope. Find slope given a table. In other words, something that looks like that T-chart or a bunch of data where we've got X, Y combinations together. We're going to be able to find slope when we have just an equation. Thankfully, 2 of the 3 forms of our equations have the slope already in them that we can identify. Wherever we see M, we know what the slope is. Standard form doesn't give us that, but we can figure it out with some extra work. We're going to have to learn how to find slope from a graph. The 4th one here, finding slope from 2 points, that's the calculation formula, y2 minus y1 over x2 minus x1. So there's a lot of different ways that we'll be dealing with slope. From an equation, this is the easy one, slope-intercept. It's m, the number that modifies x. That's our coefficient in this case. Here's a bunch of examples. Slope-intercept form, slope-intercept, y equals mx plus b, y equals mx plus b. I know you don't see m or b there, but those numbers that are in those positions tell me that it is that form of equation. If I took the numbers out and replaced them with m and b, I got slope-intercept form. That's how I check. That's how I know. So slope on the first one is 1 over 2. Slope on the second one is 2. -5 for the third one, -8 for the fourth one. It's just m. Just find m. That's the easy one. These are probably ones that we should pick up on next Tuesday, because these are ones that we have to calculate. And I'll do one of them here real quick anyway, just to give you a little taste of it. Because everybody's been wondering why we got to do these literal equations. 10x plus 5y equals 15. Well, this is why. This is why we have to know how to use and manipulate these literal equations, because this is a literal equation. 10x plus 5y equals 15. Now, I'm trying to get this to look like this. I need it to be in slope-intercept form. I'm trying to find the slope. So I'm going to have to convert this, which means I solve for y. Solve for y. Okay. On the side of the equation where I see the y term, I also have 10x. So I need to get rid of that. I got to get the y by itself. So let's take away 10x from both sides of this. Take away 10x from both sides, okay? Now I have 5y equals -10x plus 15. Not 51, I'm dyslexic all of a sudden. Now I didn't put the 10x at the end because I'm canceling those out on the left, because I know I'm trying to get to this format. That x term is going to go right after the equal sign. So I'm going to go ahead and start to put it in that format already. So this is another move and divide situation. To get to 1y, now I got to divide everything by 5. So I end up with y equals negative 2x plus 3. Now I know that the slope for that line is negative 2. And most of the time in standard form, that's what we're going to have to do to find slope. And a lot of times even to be able to graph it, because standard form is kind of cumbersome. It doesn't really help us with either of those. Solve for y. And so all of those standard form equations on that screen, I would have to do the same way. Move the x term, divide by the coefficient of y, simplify where necessary. And we will start there Tuesday, finding slope from a graph. So what I really need everybody to do is concentrate on getting caught up online, get that first unit test done, please. We're at the end of week 3. We got 5 or 6 weeks to go. We got 2 more unit tests after that one, and then the final. So it's good if you can stay current and not fall behind on this stuff. Questions, anybody? Looks like I got a couple of takers for some extra help tomorrow, so that's good. If anybody needs help Monday, let me know. I'm supposed to be in some training stuff tomorrow also. But I'll work through it the best I can. Have a good weekend, everybody. We'll see y'all on Tuesday.